Okay, so we are going to pick up where we left off yesterday. Light is weird. Okay, the two things, of course, that make light weird. Light is weird. Reviewing yesterday very quickly. Number one, no medium. Number two, C. Okay, the weirdness of light led many physicists at the time to very much struggle with the idea that it was basically either this guy or all of physics. As we discussed yesterday, you start to see kind of some of that breakdown towards the very end there. And so Einstein comes along, and Einstein makes two postulates. Einstein postulates. Basically, number one, at the same reference frame, physics is the same. So basically, I'm going to say for constant velocity, physics is cool. Still works. Okay. Number two, again, similar to what was over here just a second ago. We have the speed of light is c, adding one thing independent of movement of observer. So that is then to say, let's go ahead and make this a little bit smaller in case anybody wants to get that down in any particular way. That second one is to say, if you have a vehicle, pick a vehicle.
2006 GMC Canyon.
SUV. Okay. All right. You have an SUV that is traveling incredibly fast.
Yeah.
Your SUV is going 80% c. By the way, this is very commonly how we will list velocities today, and that is just some fraction of c. 0.8 c. Let me write that again. I don't think I did a very good job. Let's try that one more time. Velocity is 0.8, 80% the speed of light. For starters, who out of the observers, let's put the person in the vehicle, okay, this is a good moving SUV, okay, and the person to decide, watching this situation, who sees them going at 80% the speed of light? Person on the bottom, right? This person right here is the person that sees them going 80% the speed of light, right? Because how fast does the person inside the vehicle see themselves going? Yeah, essentially not moving at all. So this person, if they shoot a flashlight, okay, shoots light at the speed of c. So this person right here sees that the difference between the vehicle and the speed of light is about 20%. They're only missing it. They're just a little bit more. Except this person right here, boom, independent of the speed of light, still sees light traveling at c. 100% the speed of light, and as we suggested for that person, their velocity is 0. So yeah, it's a whole messy business. Okay, so then what we finished with yesterday was this whole conundrum. Have a light, the light goes up a distance of L and back down a distance of L. And I reminded you this yesterday, but let's remind ourselves again, how long would it take that light to accomplish that? Well, this is just distance over time. How far is it going to go? It's got to go L up and L back, so 2L, very good. And how fast is light going? Always C, very good. Just as a gentle reminder, how big is C?
3 times 10 to the 8th.
Nicely done. 3 times 10 to the 8th meters per second, or what is that in miles per hour? Something like 6.75, 6 point something like that, 6.75 times 10 to the 8th. Again, this is 300 million meters per second. We don't usually write it out like that, so let's do this real quick. 300 million meters per second. Interestingly enough, I was playing a spaceship game last night. Stupid dumb game, whatever. Point is, they start measuring distance in light seconds. Well, if this is how many meters it goes in 1 second, then this is the distance, 300 million meters per second is 1 light second. Anyway, moving on. All right. So now we take this situation up here, okay, and we take it and we're just going to grab it here, okay, copy using the power of the whiteboard. All right, and we make it smaller. Okay, and we put it on a train or some moving platform. Okay, so who sees it go up and down? Again, we'll put two observers here. Who sees it go up and down? No.
Oh wait, going up and down.
Up and down.
Oh, then it'd be
Who'd see this? We'd be the person on the train. Correct. So we're going to give this a name that is confusing. We're going to call this time proper. Now, the confusing thing about time proper is that you go, oh, that's the correct one. No, it's not. It's not the correct one. It's so dumb that they named it that because it makes people believe it's wrong. All right, let me give a definition to time proper because this definition is probably one of the more important things that comes out of today. Time proper is the time of the event. No. Sorry, I did that. Time measured by the observer at rest to the event. Okay. Once again, just normal relativity stuff we're going to struggle with here because don't forget, what does it mean to be at rest? No. You and I would see each other at rest, not moving. Why were we not moving? Are we not moving? No. Why do we see each other at rest?
Because light doesn't reach us yet.
No. All right. You are in a motor vehicle. You look down at your soda. You're going 60 miles an hour. You look to the gauge. You can look around. You see you're going 60 miles an hour. Your soda appears to be at rest. Why does it appear to be at rest?
Because it's also going.
Correct. Basically, at rest is what is meant when it shares the same inertial reference frame, aka fancy way of saying at rest is when you're going the same velocity as the thing. So, which observer, we've already actually answered this, which of these two observers will receive time proper? Time proper. Who is at rest to the event? This person up here. Because they are at rest to the light going up and down. All right, now let's look at the other person's perspective. Got rid of that up and down crap that we've been dealing with here. Now we're looking at through this person's eye, the three eyes that they just apparently developed. Okay, this person's eyes right here. Okay, what does this person see? They see the light go up and they see the light go down. Okay, now again, I reiterate, if this is traveling at the speed of light, okay, just some basic stuff here, okay, for normal speeds, like you and I at 60 miles an hour or 30 meters a second, I just want to show you what this triangle essentially looks like. This triangle, that's not even close enough, okay? Because if this right here is 300 million meters a second and you're going 60 miles an hour down the interstate, so this is 30 meters per second, essentially your triangle still 100% looks like this. Like, does it have an X? Yeah. But are we going to be able to notice it? No. As a matter of fact, I'll do some math in just a second. The generally accepted value for where you hit special relativity is about 10% the speed of light. And we'll show that here in just a minute. Point is, underneath, like you and I right now walking around, like I told you the other day that, okay, if you look at the back of the classroom, it's 3 meters away. Do I technically see the back of the classroom now? No, I don't. But it's so freaking close to now. Let's just call it now. It's no big deal to estimate that. The fractions of the difference are so small, we're not going to be able to tell the difference, right? It's kind of the same sort of thing here. Will you get time dilation if you walk around? Yes, but I did the math on this one time. If you were born into a car that was going 60 miles an hour, okay? Or actually, I think technically you have to be on Earth first. Let's try that differently. If you were on Earth born and they put you in a car immediately, and that car traveled 60 miles an hour for your entire life. Like they filled it up, it never stopped, it never broke down. It was always going 60 miles an hour. The difference of your life because of relativity would be zero point 0.1 nanoseconds. So you're not going to notice a difference of special relativity on Earth, basically, at all. It's got to go, it's got to come from space. Again, in order to pull off this triangle, this velocity, I think I mentioned yesterday, has to be like 71% the speed of light. And the way I look at that is just simply looking at geometry. Roughly, those two, I didn't draw it perfectly this time, or did draw it great yesterday, but these two sides are roughly the same. So that would mean that this side has to be, the bottom side has to be 71%. It's just that basic triangle, square root of 2, compared to this side right up here. All right. So here's what we're going to do now. Okay. The goal now is to figure out, all right, we said yesterday that this light goes a further distance, right? We said the problem was that unlike the ball example, it can't go faster. So it's got to cover, if this distance here is L, it's got to cover more than L, but it takes more time because it still is going to take, quote unquote, the same amount of time for light to travel L because it's going the exact same speed. So it needs more time, a little bit of extra time, to cover this extra distance here. So what we're going to try to figure out is how much extra time does this take? In order to do that, we're going to look at this triangle. We're going to blow up that triangle right there, although we're going to make it bigger than what I have in this case. All right. Why is that green? You should not be green. Okay. I think that was one of my children's fault. All right. No, I don't want you to be green. We just talked about this. All right. So this triangle is this triangle right here. To compare this, we are actually going to look at distances, okay? But we're going to know all of the sides. So which of these sides, which of these three sides do we already have the distance of? Oh, no, that's not a distance. But you're not far off, okay? How could you get a velocity to be a distance? Well, distance equals velocity times time, right? So this is that new time. So how far is it going to go? Well, I'm going to go c times the total time. But over here, the total time was up and down. So since we're just going up, I'm going to divide this new time by 2. So this is the speed times the time to go up. That's how far it should go. Okay? And I'm going to put a little note on here. This is the new time, so I'll put a little asterisk. Not a little asterisk, I guess a little apostrophe kind of on the end there. It's usually what we use. All right. What other sides do we have then? This isn't necessarily 71%. We have the bottom one. What's the bottom one? You're doing the hard ones first.
Oh.
How fast is it going along the bottom?
0.7.
Oh, no, don't worry about the number. Just v.
Oh,
okay. So it's traveling at v. And how much time does it have to do that? Well, same amount of time. So that would be this new time divided by 2. Because again, we're just going half the path to get there. Yeah, you pick the hard ones first. Don't we already know how far this up and down distance is?
Oh, it's 2L.
Almost. If you're just going up.
Oh, just L.
Just L, correct. All right. Now the goal is to compare this new time right here to the time that we already have, which is time proper. So what we'd like to do is arrange this in such a way that we find 2LC, and whatever's extra should be changing that particular factor. All right, so how can we compare parts of a triangle?
Trig.
Which specifically? Which trig compares a squared plus b squared equals c squared is called?
Oh, that's the Pythagorean theorem.
That is called the Pythagorean theorem. All right, so I'm going to take a squared, this whole mess. Okay, so I'm just squaring everything inside. So that's v squared t prime squared over 4 plus, so a squared plus b squared, oops, is equal to c squared. And again, the goal, once again, is to rearrange this so that we can look for time and compare it to this time over here, time proper that we already have. All right, so we're trying to isolate time. First thing I like to do, of course, is get rid of a fraction. What can we do to get rid of the fraction? Multiply by 4 across the board. That's going to cancel here, put a 4 here, and cancel there. Cool. The next thing that we want to do is we're trying to just find the time. So let's isolate the time on one side. So over here on the left side, I've already got time. I have time here. So let's just go ahead and move that to the other side just via just basic subtraction. Now I have 4L squared, this guy, is equal to C squared times T prime squared. Oh, sorry, I don't say plus. Minus B squared T prime squared. Now, if we're trying to find T prime squared, what's the next thing I should probably do?
Divide by C squared?
Nope, not yet. We got T prime squared in 2 spots. What can I do so I only put it in 1 spot?
Wait. I got you.
It's an F word.
Oh, yeah, factor that.
Yeah, thank you for doing the right F word. All right, so we factor that bad boy out. Now, what do you want to do? Divide by this whole term. So now we have 4L squared over C squared minus V squared is equal to T prime squared. Now what should I do?
Wait, was that what you're trying to find?
We're trying to get T prime.
Oh, then it's square root.
Square root, okay? Now actually, nicely, the top square root will end up very cleanly. What is the square root of the top?
2L.
Ooh, that's going to be nice. 2L over the square root of C squared minus V squared. And now, once again, we're going to see some of that math that we did yesterday with the bridge problem. I'm going to pull a C squared out of the bottom. When I do that, I will get 2L over the square root of C squared, which of course is going to be what?
C.
Yeah, we'll get that in just a second, I suppose. Times, what's this going to be? If I pull a C squared or a C squared, I get a 1, right?
Oh,
Minus, this is that math that we did yesterday, V squared over C squared. And once again, this simplifies to 2L over C, which, if you'll remember, is, what's 2L over C? Time proper. So what I can say is this new time is equal to time proper times this whole mess. 1 over the square root of 1 minus V squared over C squared. Now, to keep our lives a little simpler as we continue, because that is very messy, we're going to give this whole thing right here its own variable. Okay? So we're going to say this is equal to gamma. Gamma is basically like a V with a circle on the bottom. Gamma is equal to 1 over the square root of 1 minus V squared over C squared. Gamma is known as the, and so, sorry, let me finish my thought here. This right here. This equation is known, this concept is known as time dilation. Time dilation. So I'm going to give you some practice math with this because we're just going to do the most basic math so we can kind of understand a little bit better what we've got here. Okay. First thing that I want you to try to do, okay, and I'll work it out with you, is let's figure out what gamma is. What is gamma for something going 80% the speed of light? Okay. So if I had, let's go to another page actually here. Okay. Writing down our important equations, we have time proper is equal to 2L over C. Actually, we don't really need that much anymore. Okay. Time dilation is equal to time proper times gamma, where gamma is equal to 1 over the square root minus 1 V squared over C squared. So if I said to you, an object is going, a spaceship is going 80% the speed of light, I asked you, what is gamma? Excuse me. All you should have to do is use this equation to plug in. So we have 1 over the square root of 1 minus. Now, instead of v squared, I'm going to write 0.8 c squared over c squared. Now, you'll notice that you might say, well, Spano, I could just take, I know what c is. I can multiply 3 times 10 to the 8th and figure out what the exact number is, and that's a big, crappy number. Okay? The nice thing about, you'll notice with this math right here, is in just a second, this is going to become this. 1 over square root minus, what's 8 squared? So 0.8 is going to be 0.64 times, you can see that little guy right there, c squared over c squared. And what are the c squareds going to do? Cancel. Now, you're welcome to punch all this in your calculator. You don't need to write all that steps out, but I did want to show you kind of that particular process happening. So feel free to punch this in your calculator, or actually, you can do some of this in your head. What is 1 minus 0.64? 0.36. Okay. What is the square root of 0.36? You can actually do this one in your head. Square root of 36. Close. 0.6. So we have 1 over 0.6, which ends up basically as 5/3. Okay? If you don't like that one, this is 0.6 is 3/5, and so we're just flipping it, right? 5/3. Or 1.67. So to go 80% the speed of light is to change your original time by about 67%. So yesterday I gave you an example where I said, hey, Spano wants to be your age, blah, blah, blah. And I said 1 year for me would be 24 years for you. Now, gamma is a big crappy kind of equation right here, but honestly, there's an easier way to remember what gamma actually is simply in this equation right here. I'm going to take that equation and I'm going to rearrange it so that you get this. Time dilation over time proper equals gamma. So what is gamma? Gamma is the ratio. Gamma is the ratio of how much time has changed to how much time would be if there were no difference between us whatsoever. So what was my gamma factor yesterday when I wanted to go your age? Well, I said I was going to get 24 years, and you were going to get 1 year. So what was your gamma? No. 24 divided by 1 is 24. Yeah. And you'll notice that what are the units on that? It is unitless, right? Which is why I said also yesterday that 1 second for me would be 24 seconds for you, 1 minute for me, 24 minutes for you, blah, 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 1 month, so on and so forth. Now, you could, of course, reverse this process. The math is a little complicated, but I think we can manage right here and ask, all right, if gamma is 24, if Spainauer wants to pull this off, see if you can't take 2 minutes to figure out how fast does Spainauer have to go in order to get a gamma factor of 24. I'll give you guys a minute or two. If you're watching this video, you can skip ahead a minute or two. You good?
Yeah.
What's the first thing you did?
Trying to find velocity.
No. So algebraically, what's the first thing you did?
Multiply or root of square root.
Okay, so
Square both sides.
square both sides. I like it. Okay. Gamma squared equals 1 over 1 minus v squared over c squared. What's next? Can I tell you the easy thing to do next? Just flip both sides.
Oh, okay. Gotcha.
Next thing I'm going to do is try to get v by itself. So, okay, you can subtract 1. My personal preference, usually since it's already negative, I try to make it positive but you can subtract 1 and throw a negative across the board. Both will work. Okay, let's subtract 1. So you get minus 1 plus 1 over gamma squared equals negative. Just don't drop that negative, because what do you have to do now? You got to make this positive. So how are you going to do that?
Add it to the other side. Wait, no.
You could. We already moved the other guy to the other side.
Yeah.
That's what I would have done originally. I would have added this to the other side and this to the other side and subtracted that. But this is fine. We're here. Just basically just multiply a negative across the board. What's that going to do? This is going to become positive. That's going to become negative, and that's going to become positive. All right, what now? Multiply by c squared. And so now here's what I'm going to show you to do. You square root just this piece, because the square root of c squared is just c, right? Yeah. And everything inside right here is going to give you the fraction. So we said we wanted gamma to be 24. So calculate now with this equation, how fast does Spainhour have to go in order to get a gamma factor of 24? If you take 1 minus 1 over 24 squared and square root the whole thing. One minus 1 divided by 24 squared. And then square root it. Don't forget that. Yeah. Spainhour has to travel at 99.91% the speed of light. Stupid fast. And I think I mentioned this yesterday. The energy required to pull this off would probably energy bankrupt the entire world, so probably not the best idea. Also, blah, blah, blah. My children would be 24 years older and have lost their father for, whatever amount of time. I guess they could come with me. There's no problem with that, per se. I guess anyway, not important. Okay, so earlier I mentioned, by the way, that 10% the speed of light, 10% the speed of light is like the cutoff usually for what you consider special relativity, even at really high speeds like electricity deals with, at something like 1.2 million meters per second. That is still a fraction of the speed of light, and so it really doesn't count. At 10% or 30 million meters per second, if I plug that into this equation, just to show you real quick, 1 over 1 minus 0.1 c squared over c squared, square root the whole thing. I think this ends up as 1 point, I'm trying to remember exactly, but square root 1 divided by that answer. Yeah, 1.005. Meaning, at 10% the speed of light, the effect that we're going to get is a 0.5% difference, right? 1 year for me is slightly, what is 0.5% of a year? 0.005 times 365 days. Okay, so a year for me, a year for you would, no, I said it back, I was right the first time. A year for me is a year plus 1.8 days for you. Okay, so at 10% the speed of light, would you probably be able to notice that a person is about 2 days older than they're supposed to be? Probably not, no. So 10% the speed of light is usually the cutoff. Above that, we consider special relativity. Below that, yeah, not really. So you've seen in these examples right here that at 80% the speed of light, you get like 67% more, right? You can use this math here to see that in order to get my 24, I've got to go something ridiculous in order to pull this off. Okay. Now I'm going to discuss with you what's known as the twin paradox. Now, very, very important fact about special relativity. A lot of this feels weird, but that doesn't make it paradoxical.
Yeah.
Okay? So, for starters, I'll just tell you this ahead of time. It's still going to mess with you, but the time dilation that we've already discussed is not paradoxical. 100% accurate, 100% happens. We have to deal with it with GPS satellites all the time. Their clocks have to be reprogrammed because they are going too fast and it does get some slippage. There's some other examples that we can potentially talk about, but this definitely does happen. The twin paradox is this, okay? Let's start off with this guy. Actually, I might not get to the paradox part of this. We'll definitely get to it first thing tomorrow, okay? You've got two twins here on Earth. Let's say they're both 20 years old, okay? Apparently they're astronauts at 20 years old. Congrats. 30 years old. We'll make them a little bit more experienced. So this is Speedo. Speedo is going to get in the rocket ship, and the rocket ship is going to travel 80% the speed of light. We already learned earlier that 80% means 1.67 or 5/3 is gamma. Okay, now Speedo is going to take off and he's going to go to a planet that is 6 light years away. 6c. Okay, 6, by the way, being years in this particular case. And by the way, the reason why this equation works is just simply this. Distance equals velocity times time. Right now, yeah, the time is 6 years, c is, okay, you get the idea. Then he's going to come back. Okay, now, that total round trip should be how far? In terms of c,
12c.
Should be 12c, right? Going there and back, he should travel a distance of 12c. Okay, since he is traveling a speed of 80% speed, see, this is just, by the way, time equals distance over velocity. Distance divided by the velocity. The velocity is 80% c. We'll go ahead and cancel those out. Okay, and remember, this is years up here. This guy technically doesn't have a unit. Okay, is 0.8. What is 12 divided by 0.8? Use your calculator. It's I'm worried about. What'd you get? 15 years. Okay. But here's an important thing. We also have go slow here. So go slow is going to stay here on Earth. Okay? Who would see the 15 years? Well, let's back up to about the beginning of today when I regularly was talking to you about this thing right here. Which one of the two people in the example with the train, where'd my train example go? Okay, all the way up here. So we've got my two people here, this person and this person. Who sees time proper? Nope. Who is at rest to the event? The person on the ship, on the thing, is at rest to the event. The event being light going up and down. Okay? Who is moving, air quotes here, sort of, but who's moving relative to the event? Yes. It's messy business here because of relativity. But yes, this person's moving, so this person gets time dilation, and this person gets time proper. Okay? One more question. Who sees this velocity? This person does. Okay, so going back to the twin paradox, who sees Speedo go 80% the speed of light?
What's the other guy's name?
Go slow.
Go slow.
It's kind of Speedo, fast, go slow, staying slow.
Yeah.
Okay, they're Russian. All right, so in other words, who would see this time?
Yeah,
Go slow. And the event is the spaceship going out and coming back, right? So who's at rest to the event? Speedo. So that means go slow, this thing that we just measured here, is time dilation. So let's see how long it took Speedo to go. Well, we know time dilation is equal to time proper times gamma. So if we want to know time proper, we would just go, all right, time dilation divided by gamma equals time proper. Time dilation is, we just said, 15 years. And we measured earlier that gamma is 5/3. So doing some simple math here, 15 divided by 5 is 3. Times 3 is going to get us 9 years. So both of them started off as 30 years old. Go slow is now how old?
It's 45.
45. Go slow is now 45. With the few more aches and creaks in their bones that come with it. Speedo is how old?
39.
39. Now the twins, who got the right time?
Both.
Yes, they are correct. Are they actually different ages?
Yeah.
Yes, 100% they are. Yes. So, again, here's what's weird about the twin paradox. That's not the twin paradox. That's not the paradox part of it. That's just time dilation. And as I said at the heart of this, that is not on the table. This next piece that I'm going to discuss with you is going to be confusing. I'm sorry for this. Also not the paradox, but it is very weird. Okay, it's weird to kind of get paradox being the next statement is going to be true, the last statement was false, right? Paradox don't make sense until you try to. What's the solution to the paradox? We kind of had a paradox earlier with throwing the ball in the air. How can the same event, the exact same event take different amounts of time? Blah blah blah. Okay, so let's go to here. Going back to the beginning of today and the end of yesterday. Einstein's rules. No, that's not the beginning. That just reminds me to record. Okay, Einstein's postulates were this. We've been very much focused on the second one. C is independent regardless, and that again results in time dilation and crappiness. We haven't really focused on this. Physics is cool for a constant velocity. Everyone, for their own frame of reference, should agree that physics works. So, again, I want to remind you, this next thing is weird. It's not paradoxical. So go slow is ticked off because he lost 6 years somewhere. He goes, okay, I see that you've got a little bit more, you've got a little less gray than me. I'm annoyed. I got more. What the heck do you mean? I've done the math. This math is some of the most basic physics math that there is. And Einstein says the rules of physics, this rule should 100% be true. Okay? So he goes, it's basic math. You went 6 light years and came 6 light years back. That is a total of 12 light years. You were traveling at 80% the speed of light. So it absolutely better take you 15 years. How on earth did it only take you 9 years? This physics doesn't work. Einstein says the most basic of physics should work. And Speedo corrects him and he says, but that should only work for people going the same velocity. Because here's the deal, brother. For me, when I got on that spaceship and I was looking out the window and I was checking my odometer on the dials right here. When I went to that planet wasn't 6 light years away. By going at 80% the speed of light, the planet was actually only, trying to do some math in my head real quick, 3.6 light years away. And Gustav goes, what the what now? And he goes, yeah, follow my math. I went 3.6 light years that way, and 3.6 light years that way. So I went 7.2 light years, just like you said. You said 12 light years, but 7.2 light years. Divided by, I agree with you, my speed was 80% the speed of light. And if you would, real quick, help me out here. What is 7.2 divided by 0.8?
No.
Oh, crap. So it should only take me 9 years. Okay, so now we enter into the second part of relativity. Not only does going faster make time change for relative observers, the actual distance to a location, distance period across the board, changes by this exact same factor. This is known as length contraction. And here's the equation for length contraction. We won't develop it like we did the last one. Length contraction, which is known as length, kind of that little asterisk up there, is equal to length proper divided by gamma. And as I mentioned at the heart of this, time proper was the time measured by the person at rest to the event. This is the length or distance measured by the observer. It's not how you spell by. Try to combine by and observer at the same time. By the observer at rest to the length. So you might have asked how I got the 3.6. I've done this math already. You would not have known that ahead of time. So, who is at rest to the planet? Who is not moving through that distance? Is it speedo or go slow? Go slow. So if you'll remember, by the way, speedo got time proper because he was at rest to the event. Yeah. Go slow gets length proper because he's at rest to the length. So who gets length contraction? Speedo does. So if you want to understand where I got the number that I got, it's actually just this. The length proper is 12 light years divided by gamma 5/3. Do that for me if you would real quick. And of course, half of that is the 3.6 that we got just a second ago. All right. We're almost at the end of class. And we have covered the following things. There's a lot that we have done today. Sorry for those people that missed it. Okay? The first thing that we did is we reminded ourselves, of course, why light is weird and Einstein's postulate, and out of that, we did this whole conversation. And we figured out how much time has to change in order for this particular occurrence to happen. Like we said at the beginning, light's got to go the same speed. So if it has to go further, it's going to take more time. Now that's going to be for the person observing this larger distance. So that's this person right here. Time proper is the time at rest. Okay. Then we came over here. We practiced a little bit with this to understand kind of some just basic numbers, some context of how big certain things are going to be. 80% the speed of light, which is 2.4 times 10 to the 8th meters a second, really fast, only has a gamma of 1.67, right? And what is gamma? Gamma is the ratio of how much time that you're going to get in time dilation versus how much you would have. So what does it mean to have a gamma of 2? The person's going to get double the time on Earth. Go slow would get twice the time on Earth that speedo does. And then we saw here 10%. 10% is not going to do much, so above 10% is what it takes. And we saw, of course, how much speed Spainhour has to go to pull off that gamma factor of 24. The last part of this is the twin paradox, and I keep ad nauseum saying a very important thing. Twin paradox is not time dilation. It's not. That's not the twin paradox. Time dilation, that's just accepted, 100%. It's also not length contraction. Weird, sure, but that's not the paradox. The paradox is this. The paradox is relativity says which one of these people is moving and which one is at rest. From what perspective? Right? From speedo's perspective, sorry, from go slow's perspective, Speedo goes out and comes back. Okay? And the planet stays here. But, so that was from go slow's perspective. Go slow sees the rocket come out and come back. But Speedo knows he's moving the same way you know you're moving in the car, right? This doesn't move, and this goes out and comes back. If these paths are symmetrical, why on earth do you get an unsymmetrical result? And we will finish that tomorrow. Hope you guys online enjoyed this.